Okay, hi everyone. I will be talking about how we perform text analytics here at Megaputer, i.e. Computational Linguistics 101. So this session we'll be talking about the linguistic challenges of analyzing text data and what our approach to text analytics looks like. So before we talk about how text analytics is done, let's first just briefly address the why of why we do it. So while structured data may be easier to obtain and analyze with basic tools, only having predefined categories may pigeonhole the responder, and you might miss relevant unanticipated information. On the other hand, unstructured text, when you solicit open-ended responses, you're more likely to get more complete and detailed information that will give you more business insights from your data. Structured responses can show you what's happening in your data set, while unstructured text can tell you why it's happening. Because text format improves the quality of the data that companies solicit, and because data storage is at an all-time high, like Sergey mentioned, we have a lot more of it than in previous years. And as he said, only about 20% of the data available to us is structured, and 80% of it is unstructured. So if we're gaining value from analyzing only 20% of the data available to us, how much more can we get out of analyzing all of our unstructured text? With data storage more freely available than ever, companies are better able to store richer data in the form of text, and by analyzing it, can make much more informed decisions. So why do we need text analytics? Why don't we read all this data manually? Well, having all of this data is the same as the problem. We have a lot of data to go through. A company might have tens of thousands of records like this one coming in on a regular basis. This is just one medical device event report from the FDA's database, reporting that a patient was harmed because of inaccurate glucose monitor readings. And to go through all of that manually just to find that out is going to take a lot of time, especially over thousands and thousands of records. The process can be time-consuming and labor-intensive, so if the company wants to respond to emerging issues, that response might be delayed if your insights are delayed because you're having to read through all of this data. Also, hiring an industry expert to read and classify these would be very expensive, so you're going to have to provide knowledge training to the people who are reading through all of this. Along the same lines, this process is prone to errors. Imagine reading thousands of these full-time, week after week. You're going to start making errors either from fatigue or from lack of industry knowledge. Another downside to manual analysis is that if your goals change later and you want different classifications, your readers will have to read through all of that data again just to add the new tags, where having a text analytics system can just read through all of it again much, much faster than a human and do that for you. So that brings us to how we do text analytics. We start with text data and we put it through four main steps. The first is data cleansing, which is preparing your data for analysis. So this involves things like removing duplicate entries and empty or corrupted data, correcting spelling and grammar. A lot of text analytics systems will skip this step, but it's very, very important because your analysis is only as good as the data you put into it. If you don't have clean data, your end results will be less accurate. Step two is data-driven analysis, or statistical analysis that allows the data to speak for itself. The computer can discover some unexpected connections, notice patterns for you. But then we put it through step three, which is analyst-driven analysis. So we build on those insights that we gained in step two by using directed queries to transform unstructured text into structured data. A lot of text analysis systems will skip this step or only let you do simple keyword searches, and that's a huge mistake. We need the ability to accurately query our data to get the most value out of it. Using rule-based approaches instead of just statistics can also improve your accuracy by 20 to 25%. Step four is everything that you do with all that structured data you just gleaned. So statistical analysis using machine learning techniques to create predictive models, visualizing your results, and so on. That's all very important, but it won't be part of this presentation. We're going to focus mostly on issue-specific text data, which falls primarily in step three here. So if I may, let's take a brief linguistics intermission to talk about what kinds of linguistic knowledge are needed to accurately query text data. There's a lot that goes into reading comprehension, both for humans and for computers. So let's start with the human side of it first so we know what we need to understand written text. This is a sentence in Malayalam, a language spoken in India. No one here speaks it, right? Perfect, okay, that was the goal. So we could do this in English, but let's do it in Malayalam to force us to break it down, everything that we need to understand written text. So what's our first barrier to comprehension here? What do humans need to understand this?
What the symbols represent.
Right, we don't know what all these symbols represent, we don't know where the words are. So that's called the lexicon, or your internal mental dictionary of all the words in the language that you know of anyway. So unfortunately, none of these three words is in the lexicon of Malayalam, but the parts marked in blue are common suffixes, and the parts in black are words in the lexicon. So I'll go ahead and give you those. We have the words kid, civet, and follow. So the next obvious question is, what do those endings mean, right? So that is morphology, or the internal structure of words. So suffixes, prefixes, any way that you change a word to add meaning to it. That's morphology. So in this case, we have three suffixes. The first is the plural, so it turns kid to kids. We do the same thing in English, we just add an S to the end of it. The second one is an object marker to say it's the object of the sentence. And the third is a progressive, so it's following instead of followed or follows. Now that we have all the words, our next question should be, what does it mean? Do we know what all these words mean? A lot of people probably don't know what a civet is. So we need to know what the words mean to be able to understand the sentence, and that is semantics. So just meaning of language. Now I've put it over here on the left, touching on lexicon and morphology, because there's an interface with both of them. So your words have meaning, and your morphology, just the way that you change the words, those have meaning too. To answer the question about a civet, it is a small mammal in the mongoose family. What is the last thing that we need to understand in this sentence? What's our final barrier to comprehension here?
Syntax.
Right, syntax, exactly. So we don't know what the word order is. In Malayalam, the word order is subject, object, verb. In English, it's subject, verb, object, so I ate ice cream. By knowing the word order in Malayalam, we know that kids is the subject, civet is the object, and we kind of cheated because that's available in the morphology, but if you didn't have that suffix to tell you that it was the object, you would still know because of the syntax of the language. And then following is the verb. So in English, this sentence would be the kids are following the civet. So these are the four areas of linguistic knowledge that we need to understand written text. Let's just do a quick exercise to see how fast we go through all of this, because you do that every single time you read, even in English, or whatever your native language is. But you're doing it so fast that you don't even think about all of those different things that you have to process. So I'd like you to look at this example sentence I'm about to give you. It's a medical example, so just spot the side effect of the medication as fast as you can. It's not a trick question, just find the side effect and let me know when you found it, and I'll time you to see how fast you can do it. Okay, 3, 2, 1. Okay. Found it, great. So that was about 3 seconds. Now, you just accessed all of these areas of linguistic knowledge and processed the whole sentence in a matter of nanoseconds, but it took you 3 seconds to actually get sentence from the screen into your brain. And that's not counting the time it would take you to type or select the answer if you were trying to do this manually. So computers may never be able to understand that sentence the way that you just did, but we can teach them to mimic what you just did in order to answer questions much more quickly than we can. So I baselined this task, and PolyAnalyst answered that question for 36,000 similar records in 11 seconds. That's about 10,000 in the amount of time it took us to do one. So it's certainly much faster than us, and it could even be more accurate than human decisions if we were trying to go through 36,000 of them. So let's step through each of these individually and talk about what computers can do to mimic this behavior. Starting with Lexicon, remember that's your dictionary of all available words and what they look like. So in all of this, the computer is just seeing symbols. It's seeing ones and zeros. A lowercase t is different from an uppercase t, is different from a space, and it doesn't understand any meaning behind any of that. First, we have to tell it where the words are. That's called tokenization. So we take the individual words and phrases and punctuation marks, and we store them in a structured form for further analysis. All the rest of our text analysis techniques are based on these tokens, and it's fairly straightforward in English. We just have a basic word split along spaces. There are a few exceptions, so contractions need to be split, I'll becomes I will. Idioms should not be split, so jump the gun only really makes sense as a single unit. This is a much more challenging task in languages like Chinese that don't split words according to spaces, and you need context to distinguish where the word breaks are. So each language has its own unique challenges. So we support 15 major world languages, taking the linguistic features of each of them into account. But for now, let's return to lexical tasks as they relate to English. And arguably one of the most important lexical tasks is part-of-speech tagging. Now this doesn't seem like an important task because our brains do it so quickly we don't even think about it. We know that patient is a noun here. But to a computer, the adjective patient, a patient person, looks exactly the same. So we need that information to be able to get any meaning out of these sentences. So PolyAnalyst uses a machine learning algorithm based on statistical frequencies of words and parts of speech, and it uses word context to help determine what the part of speech is, supplemented with some rule-based tagging to improve accuracy. Just like clean data is the foundation for everything that follows, having accurate part of speech tagging is vital for morphological and syntactic analysis, both of which we'll be discussing next. So to move on to morphology, when you search for the word infuse, for example, which we have in this sentence that we've been looking at, you want to capture all of its forms, including the word infused, which appears here. You also want to capture infuses, infusing, and the word infuse itself. You don't want to capture confused, even though it looks very similar to the word infused. It's not just that these words are similar, it's that they're similar in a very particular way, with specific meaning attached to them. So like the past tense ed. And these are all forms of the same dictionary entry, or lemma, which is the word infuse here. So we call this process lemmatization. So we can use basic algorithms to strip off the suffixes to get the lemmas here, but these stemming algorithms can remove too much for words that just happen to match these patterns, like the word ring ends in ing. We don't want to turn it into the word It doesn't make sense. So we need to add some lexical information to do this properly. So for example, when you have your regular forms like go and went, there's no surface similarity to help you figure out what the lemma is for the word went. So we need to add dictionary entries to help us know what the lemma is. We also need to take into account part of speech information. So the word filling, if it's a verb, like I'm filling a bucket, the lemma is fill. It's the verb fill. But if you have a noun, like the dentist gave me a filling, you can't break it down any further. The word is filling. You can't just take off the ing. So the lemma is filling. We need that part of speech information. Lexical and morphological information are both needed for a computer to do basic text analysis tasks like counting keywords and extracting information based on these lemmas. They're also needed for indexing. Just like an index in a reference book can help you find things faster, internally listing words and their positions speeds up text processing and allows abstract searching over lemmas. So this is a process to help us search through our data set faster. Let's take a look at an example so we know what we're talking about. So take the sentence, kids love candy. If we were to create a basic index or a forward index for this sentence, it would look a little something like this. So the first character is position 0, and that's where we find the word kid. And it takes up 4 characters. So from position 0 to 4 is the word kid, or the lemma kid. And we might have information like what form it takes, like kids here, but this is just a simple look at what it's going to look like. Position 5 is love, it takes up 4 spaces. Position 10 is candy, it takes up 5 spaces. Now, if you've ever had to use a table of contents to find something in a reference book, you know that searching by position can be a little slow. So advanced text systems like PolyAnalyst use something called an inverted index, which is where we sort by word instead of by position. It's easier to search through a list of lemmas if they're alphabetized than if they're just sorted by position. So this takes more processing time to create because you have to alphabetize everything. You're going to have a lot of duplicates, like the word kid is probably going to occur multiple times in this imaginary data set we have. But it can greatly increase your search speeds, so it's well worth doing if you have a large data set. PolyAnalyst does this in the background, and I'll talk about that in a minute. First, let's move on to semantics. So when you skimmed this sentence to find the information you were looking for, you knew automatically that patient is a person, lemtrada is a drug, muscles a part of the body, pain is a bad thing, and it could be a side effect. If you were to take the word persistent out and swap it for constant or ongoing, the sentence would mean basically the same thing. But a computer is symbolic. It doesn't understand that some differences are meaningful and some aren't. So advanced text systems like PolyAnalyst can apply knowledge systems, or ontologies, in the form of structured dictionaries that contain this sort of semantic knowledge in word relationships. So we can tell it that an adverse reaction is the same sort of thing as a side effect, and that muscle pain and headache are hyponyms or types of adverse reaction. This allows the computer to draw similarities between non-identical records when we tell it how these words are related to each other, which differences are meaningful and which ones aren't. We can also define word classes with lists of words that have similar semantic and syntactic function. So they occupy the same place in a search pattern. We have words like infuse, inject, administer, dispense. They're not exact synonyms, but they all mean basically to give medication to a patient. So they're close enough for the sorts of questions that you're trying to answer when you're looking through your data set. These are completely customizable to your data set or your domain, so you can get much more targeted results with PolyAnalyst than with an out-of-the-box text analysis system that doesn't give you this sort of semantic knowledge. You can also add sentiment knowledge. You can use sentiment analysis to determine how customers feel about something. So if a customer is experiencing muscle pain after taking this medication, they probably had a negative experience with your drug or with your company. Let's go ahead and move on to syntax now. And just to get a look at how important syntax is, let's take a look at two example sentences. The first is, I would like to see a bigger hospital in town. We're talking about a bigger hospital, right? That's obvious because we have the phrase bigger hospital. But in the second sentence, they need a bigger hospital x-ray machine. We're no longer talking about a bigger hospital, even though we have the same phrase in the sentence. We're talking about a bigger machine. And hospital and x-ray are just kind of describing the type of machine you're looking at. So you need syntax to be able to tell you what words are referring to each other, what bigger is referring to. Is it referring to hospital or is it referring to machine? So the first thing that we can use to model sentence structure is called constituency parsing. This is based on current linguistic theory about how humans produce sentences, and it looks really complex. You don't have to understand exactly how it works right now, but the general idea is that you have hierarchically structured phrases when you create sentences. So you have noun phrases like the patient or persistent muscle pain that are built around those nouns. You have verb phrases like experiencing persistent muscle pain. Okay, there's a hierarchical structure to it. Now, the one downside is that this system works best on well-formed sentences, because the idea is when you create a good sentence in English, it's always going to fit into this hierarchical structure. But if you have customer responses that might be grammatically incorrect, they have incomplete thoughts, run-on sentences, and so on, this sort of analysis mode breaks down a little bit. So we can use a simplified version of constituency parsing called chunking. And that, you don't have to deal with the hierarchical structure, you're just looking at sequences of phrases. So the patient is a noun phrase, we take the sequence of verbs is experiencing, we call that a verb phrase, and then persistent muscle pain is a noun phrase. This is faster and easier to use, and it's sometimes all we need when we're analyzing text. In grammatically incorrect sentences, that normal hierarchical structure can be broken, but these basic low-level chunks will always be there. Otherwise, the sentence just won't make any sense to the reader or to the writer, honestly. Now, there's one more problem that these two syntactic methods cannot solve well, and that is words that are different distances apart that have the same meaning. So in this sentence, the patient developed an unusual ringing sensation in his left ear and blurred vision. The patient developed blurred vision, but we don't have that phrase there to tell us that blurred vision is something that the patient developed. So it can be difficult to use constituency parsing to follow that tree down and to capture these sorts of relationships in text queries. So we need another type of parsing that captures these meanings by helping us find objects of verbs, what noun and adjective refers to, and so on. That brings us to dependency parsing. Again, you don't have to understand exactly how it works, so I'd be more than happy to explain it to you later if you're interested. But the idea is that we have relationships between words no matter how far apart they are. So the subject of the main verb is patient, so we see that subject relationship identified. The object of experiencing, what the patient is experiencing, is pain, so we draw a line marked object from the verb to that object. And then what kind of pain? Well, we have modifier relationships that say it's persistent pain, muscle pain, and so on. So this will help us solve those sorts of problems with syntax. Syntactic analysis is one of the many features that makes PolyAnalyst unique. This is not something that other text analysis systems are using. When we do a thorough analysis of word relationships, when we develop our text queries, we can get much more accurate systems than by using out-of-the-box text analysis systems. So another thing that makes PolyAnalyst unique is its ability to apply any or all of these linguistic methods to let the user target very specific linguistic structures and conceptual patterns. So when language meaning, form, and structure are combined, we get more information extraction power. By using all of these linguistic areas, we can extract a remarkable amount of meaning out of these thousands and millions of characters that the computer's just reading as ones and zeros. Another benefit of using a cohesive system like PolyAnalyst is that we can use these linguistic principles without being concerned about how they work. So I'm kind of explaining the underlying process between under text analysis, but you don't have to know exactly how it works. PolyAnalyst has a single automated step for all of these lexical, morphological, and syntactic tasks. So in the lexical realm, we do that tokenization. We identify all the words and part of speech tagging. There are other things that we do too that I don't have time to go into. We do morphology work in lemmatizing all of those words, identifying those underlying dictionary forms. All three of these go into our indexing process once we have that lexical and morphological information, so we can search through our data much faster. And then we apply our syntactic knowledge, do all of that syntax parsing, constituency parsing, dependency parsing, all those things I just discussed. You can also access default semantic information that's already available to you. It's built in and ready for you to access, or you can add your own that's more relevant to your data set or your domain. All of this work is done in the background simultaneously, so you don't have to worry about how they're done. You just have to know how to apply them to get the results you want. Now, before we finish, there's one more thing that we can use to give computers a leg up. When you read through that sentence, you were skimming for words that were significant, right? So your mental lexicon also contains information about significance. So things that your eyes are drawn to when you're scanning for information. Computers can mimic that powerful effect of human cognition with statistics. So there are a few things that we can do in the realm of statistics to make our lives easier. We can do frequency analysis, so counting up how often a word occurs in our data set. That sounds really boring, but when you take it in combination with background frequency analysis, things get more interesting. So your background frequency analysis is how frequently the word appears in a similar data set, either a general data set or one that's just a different data set in your same domain. We contain all this information in statistics dictionaries, so that statistical information, how frequently those words appear, that's all built in for us. And we can apply that knowledge to do frequency deviation analysis. That's what we do when we do keyword extraction. So if a word appears much more often than it should, based on our knowledge of the background frequency of that word, then it's much more likely to be a keyword for your data. We developed this algorithm by analyzing tens of millions of documents, so it's working pretty well. Now you can also do key phrase extraction after you've extracted these keywords. So you can look for key phrases for your data set. So if words appear together much more often than they should, they're more likely to be key phrases for your data. Now all of this is, all those statistical linguistic features that we just discussed are what we use to do analyst-driven analysis. It's also called supervised analysis, and we use it to realign the results of our unsupervised analysis to better reflect our business objectives. We can use linguistic and statistical information to create more accurate queries, and by doing that, we can do tasks like classifying text documents and extracting information quickly by combining expert knowledge with computational processing power that we get from that statistical analysis. Now, just to do a review of all that linguistics that we just talked about, we start with the lexicon. This is the same sentence that we've been looking at. We do tokenization, split up all those words to use them for text analysis. We do part of speech tagging, so that we can set that foundation for everything else that we do in morphology and syntax. We lemmatize the data using all that information, identifying underlying dictionary forms of all the words that appear in the data set. So experiencing is a different form of the word experience. We index the text so we can search through it much more quickly. And we add semantic knowledge. So Infuse is a method of dispensing medication, Lemtrada is a drug, muscle pain is a possible side effect. And then from there, we can start doing syntactic analysis. So patient is the subject of infused, so we know that someone was given that medication. We also know that that same person is experiencing something. The object of experiencing is muscle pain. So we know that someone was given the drug, and the same person then experienced a side effect, or whether a possible side effect or a known side effect. That, whether it's relevant or not, that will emerge as you start gathering much more data from many different records. So targeting your queries like this gives you the power to get the information that you need out of your data. This method is completely customizable and adaptable to new data sets or domains or goals, even for the same data that you had before. That is all I have, so are there any questions?
Thank you for watching. Stay tuned for more from Megaputer Intelligence.